Atomic mass versus atomic weight. What's the difference? My name is Alyssa, and it is the goal of this video to help you explain and understand these terms so that you can answer questions relating to them with confidence on test day. In this video, we'll investigate both the terms atomic mass and atomic weight. However, isotopes are an important factor to consider when talking about atomic weight, so we will of course introduce and define this term as well. After watching this video, you will understand the difference between atomic mass and atomic weight and know the importance of isotope in relation to atomic weight. You will be able to answer questions that ask you to calculate the relative abundance of isotopes based on the atomic weight. We'll start by defining atomic mass, which is the mass of an individual atom. Remember that atoms are composed of protons, neutrons, and electrons, and so the mass of an atom is a result of the sum of the masses of these different particles. However, electrons are about 2,000 times smaller than protons or neutrons, and so we do not include the mass of electrons in our calculations. The mass of a proton and the mass of a neutron are approximately the same. In fact, a proton is only smaller by the mass of an electron, which we have already stated is small and doesn't really matter in our calculations. We can report mass in grams or atomic mass units, where 1 AMU is the mass in grams multiplied by Avogadro's number. So we can easily convert these units from one to the other. Using the example of boron 10, we can use atomic mass to calculate how many neutrons are present. Boron 10 has a mass of 10 and its atomic number is 5. This means that there are 5 protons in a boron nucleus. And so 10 AMU minus 5 AMU leaves us with 5 AMU, or the mass of 5 neutrons. We know that 5 protons and 5 neutrons add up to 10, so why is the atomic weight on the periodic table reported as 10.81? This is due to the different isotopes and their abundance. Let's learn more about this. Isotopes are atomic variations of the same element. They have the same atomic number, which means they have the same number of protons and electrons regardless of the isotope, but they have a different atomic mass, and therefore the number of neutrons is different. We'll again use the example of the element boron and look at the number of protons and neutrons as well as the isotope abundance. We know that both isotopes of boron have the same number of protons, but the number of neutrons is different. Remember that boron 10 has 5 neutrons. And using the same procedure that we used previously, we can see that boron 11 will have 6 neutrons. Now these isotopes occur naturally, but the amount of a given isotope that's found in nature can vary. The abundance values mean that in 1 mole of boron, 80% of the atoms are boron 11 atoms, and 20% of the atoms are boron 10 atoms. But what determines isotope abundance? It has to do with the stability of the isotope. The more stable an isotope, the longer it will stick around. This is related to the half-life, a measure of nuclear decay. The longer the half-life of an isotope, the longer it will take for the atom to decay, and the more abundant it will be. The graph to the right shows the distribution of isotopes in a proton by neutron plot with their half-lives color-coded based on the scale to the right. In this graph, all the isotopes found above the diagonal line contain more neutrons than protons, and it demonstrates that isotopes are more stable when this is the case. We'll take a closer look at the element bismuth. Bismuth has the atomic number 83, and so it has 83 protons. Bismuth has many isotopes with varying half-lives, but the most stable is the isotope containing 126 neutrons. We can find the atomic mass of bismuth by adding the number of protons and neutrons just like before. We find that the atomic mass for this isotope is 209 AMU. We know that this isotope is the most stable, and so we can assume that it is the most abundant. In fact, it is, and makes up almost 100% of naturally occurring bismuth. We can see this based on how close the atomic weight on the periodic table is to the atomic mass of this isotope. More to come on this topic soon. Let's go through an example of how to determine how many atoms of a given isotope are in 1 mole of an element using the knowledge of relative abundance and Avogadro's number. This question stem provides us with that information by giving the relative abundances of carbon 12, carbon 13, and carbon 14. Make sure you take note of the large difference between the abundance of carbon 12 and those of carbon 13 and carbon 14. Remember that relative abundance refers to the percentage of an isotope in 1 mole of an element. Therefore, we can solve this question for each of the different isotopes of carbon. We do so by multiplying the relative abundance by the number of atoms per mole. This will give us the number of atoms of each different isotope in 1 mole of carbon. We can see that carbon-12 has the highest amount of atoms per mole of carbon, followed by carbon-13 and then carbon-14. Have a look at the large difference between the number of carbon-12 atoms and the number of carbon-14 atoms. This makes sense given the large difference between the relative abundances of these isotopes. We now know that 1 mole of an element contains various isotopes of different mass and in varying abundances. This can prove difficult in a practical sense when we need to measure 1 mole of an element. In these cases, instead of using atomic mass, we use atomic weight, which incorporates these isotope variations. We can calculate atomic weight using the information calculated in the previous example for the number of atoms of carbon-12, carbon-13, and carbon-14 in 1 mole of carbon. The first step is to take this number and multiply it by the sum of the protons and the neutrons. Remember that for each isotope there is a different number of neutrons, and so this value will be different for each isotope. The final step is to multiply by the mass of a proton or the mass of a neutron. Doing this calculation will lead us to the mass of each different isotope within 1 mole of carbon. Once we've calculated these values, we simply add them up to obtain the atomic weight of carbon. This is the number that we see on the periodic table. However, there is an easier way to calculate this value. Remember this basic rule for calculating atomic weight. The atomic weight is the sum of the isotope's mass multiplied by its abundance. Now we can put what we learned to the test with some practice questions. This question tests your ability to predict isotope abundance from atomic weight. The answer is C. The quickest way to solve this question is to realize that the atomic weight is closer to 35 than to 37. Therefore, it must be that chlorine-35 is the most abundant isotope. This means that our answer must be either C or D. If it were D, then the atomic weight of chlorine should be essentially 35, but it isn't, so we know that C must be our answer. We can also solve this question using the basic rule regarding atomic weight. The sum of the atomic mass of each isotope multiplied by its abundance is equal to atomic weight. Two isotopes make up 100% of chlorine atoms, so the sum of the abundance of chlorine-35 and chlorine-37, X and Y, must equal 1. We first set Y equal to 1 minus X and substitute it into the atomic weight equation. The next step is to solve for X, and we see that X equals 0.75. Therefore, Y must equal 0.25. Doing this calculation, we again see that the answer choice is C. This question asks you to use what you know about isotope stability to predict isotope abundance. The answer is D. Stability is related to half-life, and so the isotope with the longest half-life is the most stable and will therefore be the most abundant. Uranium-238 has the longest half-life of the three isotopes, followed by uranium-235 and uranium-234. Great job if you got that one correct! Before we finish, let's review some takeaways. Remember that atomic mass is the mass of an individual atom and depends on the number of protons and neutrons in that atom. Remember that isotopes have the same number of protons but a different number of neutrons, and therefore the atomic mass will be different for different isotopes. Isotope abundance is determined by stability. Isotopes with longer half-lives will be found in greater abundance. And finally, atomic weight. Remember, to calculate this value, you must know the mass of each isotope as well as their relative abundance. Thank you for watching this video on atomic mass versus atomic weight. Good luck studying for your MCAT.